Hi all. Uh,
Good evening, ma'am.
Good evening. Good evening. Welcome to the class. So I think many of you have joined this class. So we can start now as well. Right now, six, 8. Okay. Sounds good. One sec. I'll switch off the fan so that there will be no issue in voice. So one thing I would like to confirm: am I audible properly?
Yes, ma'am.
Okay. So only 4 of you have joined. So no issue. Let me check whether the recording has been started or not. Started, yeah, okay. So I used to start the recording, or I used to do the recording through OBS. So I think one of the teacher, one of the student of this class was having the problem in the recording. So I would like to confirm, like, if you have a problem in recording or a voice, then you can just go through the PDFs which I upload in the drive link, which I have shared to you in the public sheet, so that you can just see it and try to cooperate. Okay, so let's start this session. So I think up to week 5, I think week 5 is also over for you. But sir, KG Krishna sir, as instructed, we have to do according to week wise. Otherwise, it won't be counted to us live sessions. So I was very much restricted to do this one. But yeah, for sure you will learn very new concepts here as well, in addition to whatever the Aditya sir has taught you in the class. So till now we have seen AM, TSPSC, and SSB. But in addition to this, a VSB has come. So AM is the amplitude modulation. So why this DSPSC is needed, and why this SSB is needed, and in top of it, why FSB, VSB is needed. So there's having a variety of applications where AM, DSBSC, and SSB can be used. So first of all, where AM can be used. So first of all, if anybody asks you where AM can be used, then you should know the frequency band of the AM. So frequency band of the AM is 88 kilohertz to 108 kilohertz. So in that, AM is generally used for broadcasting purpose from point to multipoint, or multipoint to multipoint. So if, for example, one wants to convey any information from a large distance through a satellite or through a video, then AM is used. But also a specific purpose, specifically AM is used for broadcasting applications. Example, point to multipoint. Now, why DSBSC is used? Why DSBSC is needed? Because we in AM a lot of power is getting wasted due to the carrier power. So here it is introduced. And DSBSC is also needed whenever the AM is used. So whenever we don't have power requirements, so DSBSC is preferred over AM. And where the SSB is used. So since in SSB the efficiency is 1, so here also, wherever the AM and DSBSC that doesn't suit, the SSB is used. And SSB is generally used for a voice signal. Now I will explain why it is used for voice signal. This is very important, very often to be asked in the interviews exams, and where the VSB is used, and it is used for video. I'll explain why it is used for video signals. I'll explain why SSB is used for voice signals. So I think these things are not taught by sir. So I would like to cover some application perspective, because you should know, you are reading it and you should know the practical purpose of why it is used and why it is required. So mathematically, at page, yeah. So let us write the mathematical formulation of each and every one. So AM, DSB, SC, SS, SSB, and finally VSB. I am hoping that you have learned already this VSB. I will again go through it so that you can recapitulate it, whatever you have learned. So ST is equals to AC 1 plus KAMT cos 2 pi FCT. This is all about amplitude modulation. Later, we will see the phase modulation and frequency modulation. I will compare where the A modulation used and where the frequency modulation and phase modulation is used. So when you know these formulations, definitely you can correlate how it should be used in frequency domain as well. And DSBSC, SSB, VSB. Now tell me this answers for this one. Question, do you know?
Yes, ma'am.
Hmm.
VS. Ma'am, you are asking about VSB signal. VSB.
Yeah, VSB also. How
No,
it
ma'am.
is
No,
used.
ma'am. I don't know about that.
Okay. Okay, this is question one for us. DSBSC and SSB?
Yes, ma'am. DSB is simply multiplication in time domain. Carrier carrier signal multiplied by MT.
Yeah, SSB, tell me.
SSB is MT multiplied by cosine, and SSB will be MT into cosine, and it's Hilbert transform multiplied into sine.
Yeah, so it has two parts, right? First is a lower sideband and upper sideband. So
Yes, ma'am.
MT AC cos 2 pi FCT by 2 plus or minus MT cap by
Yes,
2
ma'am.
AC sin 2 pi FCT, right? Hmm. And
Yes, ma'am.
where the negative sign is used, it is USB, and where the positive sign is used, it is SSB. Negative for USB, positive for SSB.
Ma'am, LSB, LSB.
Sorry, LLB. Lower sideband, yeah. So here we will see how this can be defined. And we know that the filters designed for AM, DSB, SC, LSB, at the demodulation we require filter, right? Because we are converting a baseband signal to a band pass signal through modulation. Now we want again the baseband signal from a band pass signal. So band pass signal we will pass through it through it a low pass filter. Then we will get again a baseband signal, which was the actual message signal. So we will require filter. We'll see the criteria for the VSB, and it is very interesting how we can see the criteria for VSB filter and why it is used. We will have the already have SSB. Already this VSB has the this bandwidth of extra W plus FB, right? It is slightly greater than SSB. So why it is required? The question is this.
Ma'am, it is simple to construct.
Yeah,
It's
simple to construct. And I'll explain with a practical example, with a proper practical example, why it is used. So proper practical example is a video signal. We will see how the video signal it can be used through VSB. And only video signal can only be transmitted through VSB, and only this one. So that's why it is simple to construct also. We can say not simple, because the criteria for F plus FC plus H F minus FC is 1, and how it has been come, you should know. So let us go through that. First we will draw a simple diagram for the AM modulation, SSB and DSBSC and VSB. So this is SAMT, This is T, and this one is impulse signal, which is AC by 2, and then FC plus FM, FC minus FM, and this one is FC, and this is minus FC, this is minus FC, minus FM, this is minus FC, minus FM, and this is plus FM. Okay, and this one is the SB, SC, you should know, T, FC plus FM, FC, FC without carrier, sorry, it should be without carrier, and this one is FC minus FC minus FM minus FC plus FM. Why I'm writing again and again this one? Because you should remember in your mind, like what is the frequency. Sometimes it is given some value, you should know what should be the value. Now this is, sorry, it should be F, should be F, it should be F. And now tell me whether it is USB or LSB.
USB.
Yeah, okay, nice, nice. You know that. So it one is SSB, USB, F, F, and this one is FC, FC plus FM, FC minus FC minus FC minus FM. So yeah, why I have written this? Let us see that. The bandwidth required for this is, what is that? 2 FM. Here also 2 FM. Here is FM. Or we can say W if we have a message signal as this one. W or FM. So many books write W, many books write FM. So I'm writing FM. It's not an issue. So yeah, the bandwidth is 2 FM. Bandwidth is 2 FM, and bandwidth is FM. So yeah, bandwidth is very costly. So this is having a higher bandwidth than this one, but if so that it has the efficiency of is equals to 1. Here we can achieve efficiency at max of 50%. Here we can achieve efficiency as max of 33%. Max, 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 100%. So yeah, we'll go through the application part. Soon we'll get to know how why I'm doing this. Uh, I hope you will love to be that. So, yeah. So vestigial sideband, which is VSB, it is different. It differs from SSB just in the bandwidth perspective. Otherwise, it is same. It requires slightly higher bandwidth at the cost of its application. So when we'll do that MTCT, here we'll get DSBSC, and then we will pass through a band pass filter, which will get VSB. But see, if it is a simple band pass filter, then we will get a SSB. Simply we are getting a two side bands, and then we are passing only a one side band, then we are getting SSB. But here we are passing a different filter so that we will get a VSB. So suppose this is DSB, which is having two side bands. Then SSB USB, how it will look? We'll have only this one, this this one. Here this one, this one. So how the VSB should be, the filter of VSB should be like this. So we want this. We want to pass this sideband in such a way that the filter has having this type of characteristics, where the area of this one and the area of this one should be same. The filter is chosen. So you were saying it is a very less complicated. So yeah, sometimes in designing this filter, which is having this area and this area is equal, is very complicated in practical scenario. So why it is required? It is required for a specific purpose. So it is shifted from SSB uh, band pass filter, it is slightly shifted. So the bandwidth of VSB is equals to W plus FB, and which is slightly higher than SSB. So how the generation of VSB should be? So it is simply MT into VT, which is passed by a band pass filter, which is having this characteristics which I had explained it, and then we'll get the VSB. Then, for example, let us consider how we'll get the VSB. So as I explained this is MT into CT, and they will pass through a band pass filter, HT, and we will get VT. So let us find this. So you know that suppose this one is VT. So suppose this one is VT, then VT is equals to simple MT into CT. CT is AC cos 2 pi of CT. Then ST is equals to VT convolution into ST. So I'm writing here any modulated signal is represented by S. So you have to write the S. So ST is equals to VT convolution of ST. And you know that in frequency domain, it is SF is equals to VF into HF. And then VF is equals to how we can write AC by 2 FC minus F minus FC plus F plus FC. Why it is that? Because VT is equals to MT into AC cos 2 pi FCT, and in right in this and in frequency domain you will have a shifted part of this one. So this is written in frequency domain, and VF is equals to this one. And if we put VF is equals to this one in SF, then you will get this. Lakshmi is asking. Yeah, Lakshmi has joined. So yes, SF is equals to this one. Now, how you will do the demodulation? So this one I'm telling you why HF minus FC plus SF plus FC is equals to 1. Then we will demodulate using a low pass filter. So SF is this one, and SF it will again be multiplied with a coherent oscillator. Coherent means the same frequency oscillator as used in modulation part. Then you will get V1T, and you will pass through a low pass filter, and you will get a message signal which was passed in a VSB generation. So V1T is equals to ST into cost AC cos 2 pi FCT, this one. Then V1 is equals to, you know, this shifted version of that. Then SF minus FC is equals to AC by 2 MF minus 2FC plus MF, because we are putting this SF here, SF here in this one from equation 1, and you will get this one. And V1F is equals to AC square by 4 MF minus F2C. I want you to calculate this one, but you will get definitely. And after passing a low pass filter, you will get this one. Since you require only a message signal at the receiver end, so this term should be constant. This term is coming along with this. So we have to design a filter in the generation of a VSB signal, so that it will have a constant this type of characteristics. So it should be constant to recover the message signal. So yes, it is in the generation of the VSB generation, you used a filter which is HHT or HF in frequency domain, and it should have this characteristics. Anyone is having doubt in this, like why it is having this characteristics? What I did a modulation purpose, then I try to demodulate so that I will get a message signal which I have transmitted to get it. Now at the receiving end, I'm getting this frequency, this component along with this MF, which is required for my purpose. So this frequency component should be equals to 1 or constant. Anyone is having doubt in this?
No, ma'am.
Okay, nice. So yeah, now if we plot this HF plus FC or HF minus FC, then suppose if HF is this one, If we shift it to this particular thing, then we'll get this one. And then you have to fit, I have to choose a filter so that HF minus FC plus HF plus FC is equals to constant. The constant can be 1 as well. If we just plus it, then it should be like this. And in a SSB generation, you use the filter where the value of the filter at FC is equals to 1. But here the value of HF at FC is equals to 1 by 2. So in the GATE exam, this question is directly asked, like how would the value is 1 and 1 by 2. So the condition is this one, and it is very important. So it is used in the VSB generation. Now we will see how this is only used for a, video signal generation page. Now tell me the frequency of video signal. The frequency of voice signal. Kirti, last class you have answered, I think.
Yes, ma'am. Ma'am,
Huh.
for voice, like human-made voice, it is three up to 3.7 kilohertz, and for video, it is 4.3 megahertz.
300 hertz to 3.5 kilohertz.
No, yeah,
Yeah.
0 to 3.7 K.
If we write it says 300 hertz. Yeah,
Oh,
up to 300 hertz, the minimum frequency is 300 hertz only. Voice. What is video? Video is 0 to,
4.3 megahertz.
yeah, 4.5 megahertz. We write, okay, this is, yeah. And I'm telling you that it is in this, it is used as SSB, and here we use DSB. Why it differs? So let us see the spectra of this. First, consider voice. You will never forget this, where this one is used and where. So Kirti was absent that time, but yeah, the AM modulation is used for broadcasting purpose, and it is used for both audio, but yeah, for a large range, because the frequency is in the range of kilohertz, so you will get a large range. Whereas in FM modulation, the frequency in the range of 88 megahertz to 108 megahertz, so you will get a very small range, so small distance. So the audio it is also used for audio signal, but AM is used for broadcasting purpose. And AM is in AM, the SSB used for voice modulation and VSB used for video modulation. Let us see why. So let us draw the spectra of voice. So MF, this is a message voice signal. Okay, I think Lakshmi left. It is a message voice signal, and it should be 6 300 hertz to 300 hertz to 3.5 kilohertz. Okay. So after modulation, suppose FC is equals to somewhat kilohertz, thousand of kilohertz, whatever. It should be greater than, very, very greater than MT. So what the spectra of modulation looks like? The modulation spectra should look like this one, right? 300 hertz, sorry, FC, it should go to FC, somewhat FC will be here, FC minus 300 hertz on FC plus 3.5 kilohertz. Here sometimes FC will looks like here, if it will get shifted by FC. So FC and FC minus FC plus 300 kilohertz, 300 hertz, and FC minus FC minus 3.5 kilohertz. So, and what is this bandwidth is? This bandwidth is 300 hertz, 600 hertz. So in this generation, you should choose a filter where you will have a abundant distance, so that you can reconstruct the message signal. So in SSB, we use this type of filter, right? So we can get this one. So SSB is used, because only this type of uh, the frequency domain a message signal looks like. So the band pass filter, so it is low pass filter, you will get this one, the low pass. Yeah, sorry, band pass filter, you will get this one. But in VSB, since the bandwidth is 0 to 4.5 megahertz, and you will have this type of spectra at after modulation, because you will not get this the space. So you should have the frequency, you should have the filter looks like this, which was HF minus FC plus HF plus FC. In the generation, you will get a video signal, proper video modulated signal. However, VSB requires a little higher bandwidth than SSB, but it is required to produce a video signal, and it's well known fact that a video signal is modulated by a VSB modulation. Okay, so those who don't know about this frequency and all, please get to know about this, because this is very important and this is required in practical purpose. We will solve the questions now, half an hour. So yeah, this is all about the VSB generation and VSB modulation and VSB frequency. Now I'll explain more about the. So anyone is having doubt in VSB part? Otherwise, I'll move to that frequency and phase modulation. Um, Kushit, you are having any doubt?
No, ma'am, it's clear up to now. Clear.
Okay. Katie?
Ma'am, actually, I just want to ask a simple question ki like why you have taken FC plus 300 hertz one time, another time 3.5 kilohertz. In
No, no, no,
general, we
no.
are
Okay, okay. Sure, sure.
considering FM, maximum frequency content, right?
No, no, no. So I'm taking this MF. MF is the spectrum of the message signal. So message signal is having the frequency of this one, 300 hertz to 3.5 kilohertz. It is in the internet as well. You will find this. It is not from 0 to 3.5 kilohertz. So I'm taking
Right.
this one. Okay. So after modulation, you know about this one. Let us see. For example, let us see this. You know that you have solved this MF. You know, after modulation, what
Yes,
you
ma'am.
see? You see,
So FC plus FM,
yeah.
yeah.
So this one is added here, and this one is added here, right? Subtracted here. The same
Yeah.
I have done. The modulation. Now I'm explaining through the filter
Okay.
why the SSB is used for voice. Because the filter is having these characteristics. SSB generation filter is having this characteristic. This is required only in one side event.
Hmm.
So that's why SSB is used. For a video signal, I told you that it is having this frequency. So it is not having any gap. So that gap is not there. So
Okay.
it is the filter should be like that, so that we can generate this one. We can have the modulation this one. Yeah, yeah, Kushit.
Ma'am, then I have this doubt that why you have taken this triangular shape of a spectrum for voice signal
Yeah,
and
yeah,
this
yeah.
rectangle.
So
Yes.
what happens now? Yeah, spectra, very important. So at lower frequency, you will have a higher amplitude. Generally, the MF is amplitude. Okay. So
Okay.
at a lower frequency, you will have higher amplitude. At higher frequency, the amplitude decreases, because either you can have
Okay.
a amplitude or you can have the frequency. Similarly, we take only triangle in MF. Everywhere we have taken triangle. So it is also having the logic, because here it should decrease. The amplitude should decrease with increasing frequency.
Okay, ma'am. And in case of video signal, it is constant.
Yeah, it is constant. We have taken
Okay.
it is also having the same, because video signal is having a mix of both. Like it is having a very high resolution. So we should have the
Okay,
amplitude as well as frequency. So we have taken this, and you will find in many spectra also. This should be like this.
okay, ma'am. Good.
So I think VSB is completed, and okay. So once you just correlate whatever the application is this, then you might not forget anything. So sometimes many people ask, what is the application of VSB? Why is this needed? If we have already AM, then why it is needed? So you should know the difference between the efficiency, bandwidth, application, and always the mathematical formulation, generation, demodulation. These things you should make a table where you can have an input of these things, and you can have output and the application as well at the last, and then you can compare in your mind, and you can never forget. So fine, I think. So I'll um does anybody know about mixer? Sir had taught about mixer in the class? No, no?
No, ma'am.
Okay.
No, ma'am.
So sir has not taught in the class of super heterodyne receiver as well. So sir will taught about these things in the upcoming classes, and super heterodyne receiver is very important. So I'll skip this mixer. So angle modulation up to what sir has taught in the week 5. KG Krishna sir, are you attending all the classes of the Aditya sir?
Yes, madam. Yes,
Yeah.
madam.
So we up to week 5 you have watched.
Yes, I have attended, but I don't say that I have understood it fully, but I have attended.
Okay, 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 okay. Okay. So till now we have seen
Ma'am,
ang yeah, Kirti, yes.
ma'am, in week 5, actually, angle modulation in that phase modulation and FM generation,
Mm-hmm.
indirect method of phase modulation generation, that kind of things are covered.
Okay, okay. Yeah.
Yes, ma'am.
Actually, there is much more focus is given on pre-envelope and complex envelope kind of analysis. Few lectures, early few videos are dedicated to that.
Yeah. Envelope, envelope. Yeah, yeah. And QCM also is taught in week 4, I think.
Yeah, QCM is also there, ma'am.
Okay, okay. So, okay. Um, I think so. Yeah, envelope is very important because it is used in the spectrum analysis. So, sir is given more emphasis on that. But okay. So, up to now, we have seen this amplitude modulation and the types of amplitude modulation and QCM, and then this comes the angle modulation. So, if we see the message signal and the carrier signal is having AC cos 2 pi fct. This one is amplitude and this one is phase. Okay, a very basic question I'm asking. Can you define this modulation? What is modulation? Kushit, can you define modulation?
Ma'am, changing the parameters, some parameters of the carrier signal as per the message signal, it may be phase, amplitude, or frequency.
Yeah, very nice, very nice. Some people confuse and say that I'm changing parameters of message signal. So we only change the parameter of carrier signal. So we can change amplitude and phase. This is very basic. Okay, so we all know that. So in angle modulation, in angle modulation you'll have two types. The first one is frequency modulation and phase modulation. So if we change the frequency FC and if we change this phi t, this will be phase and this one is a frequency. So the phase modulation can be written as ST is equals to AC cos 2 pi FCT plus KPMT. So in amplitude modulation, you added one term in amplitude, but here you are adding in term in phase cos phi plus phi dash, and in frequency you will add the term in with frequency cos 2 pi FC plus something F dash T. So you can see the change. So if yeah, so you will have the parameter of kpmt. So phi is equals to kpmt. Then I told you that the ka should be 1 by v. But what is a unit of kp? The unit of phi is radian, and the unit of mt is generally ampere or volt. So it should be the unit of radian per volt. So how you can discriminate between phase modulation and amplitude modulation, as phase modulation and frequency modulation, because there is various different various confusion between those. In the question sometimes it is not given, so you can just check the unit of kp and kf and compare and use the formula accordingly. So this one is, and this is not equals to modulation index. Yeah. So before modulation you will have only phi is equals to 0, but after modulation you will have the phi is equals to kpam 2 minus kpam, when mt is equals to am cos 2 pi fct. Am is the amplitude of the message signal. So phi max is equals to maximum phase deviation, which is it is equals to kpam. And in frequency modulation, what you will have only fc, but you will add a instantaneous or intermediate frequency. Sometimes this is called also called instantaneous, but intermediate frequency we also use the terms this. And here you will have the mixer and all those concepts later in the class. So fc plus del f you will have, or fc minus del f. So fc kf into mt, and the that one is fc minus kf into mt. So you should know, Pujita. So you should know that this constant is always multiplied with mt. The constant is always multiplied with mt. AC1 plus kmt. Now cos 2 pi fct plus kpmt. Now this one fc plus kfmt, because it should be varied according to the message signal. Now since indirect method Kirti was saying, so I'll tell that. So for single tone modulation, mt is equals to am cos 2 pi fmt. Now fi is equals to fc plus kf am cos 2 pi fmt, and fi max and fi min. I'm dealing with frequency modulation for now. So kf am is a frequency deviation we call, and similarly the amplitude deviation is kam, and the phase deviation is kpam. Okay. So Fi max is equals to Kf plus F del F. For single tone phase modulation, okay, the phase modulation is also there. Now, the difference between these two. So phase is equals to omega t is equals to cos 2 pi ft. Now, if you differentiate it with respect to t, then you will get 2 pi f. Then f can be written as 1 by 2 pi d theta by dt. Now, if you know these two formulas, then you can generate Pm from Fm, sorry, Pm to Fm, or Fm to Pm. How you will generate? If you have the frequency modulation, suppose frequency modulation is represented by Fi. I'm just saying this, it is a modulated signal. Then if you integrate it and pass to a phase modulation, you will get a phase modulation. And if you have the this theta term, theta only, free phase, then if you differentiate it, then you will get a frequency modulation. So I think sir has taught in the class of this one also. So yeah, you know that theta t is equals to 2 pi fi m t dt, and we know that fit is equals to fc plus kf am cos 2 pi fmt. From there on, fc plus fit. Yeah, it should be something different if we are writing this one is fi. So theta t is equals to 2 pi fct plus kf am by fm sin 2 pi fct. So I'm just directly going through the this one. St is equals to AC cos 2 pi fct plus beta sin 2 pi fmt, and the general time domain equation is this one. AC cos 2 pi fct plus 2 pi kf integration of mt dt. Okay, so integration of mt dt, this is the formula for Fm. And how will we get this frequency domain modulated signal? Through two method, which is one is direct one, and another one is indirect method. So we'll see that. So STAFM is AC cos 2 pi FCT plus 2 pi AFM integration of MTDT. And if it is a single tone modulation, you will get just beta, and beta is equals to del F by FM. So let us see the spectra of this one. For example, if the message signal is represented by this one signal, MT, and then CT is this one. So just that for positive part you are getting a higher frequency, for the negative part you are getting a lower frequency. So this frequency is modulated by FC, and if the frequency is FC, then FC plus del F, and here FC minus del F. Suppose, for example, I'm just repeating the concept which is already taught by Aditya sir, then you can use my concepts to revise whatever you have learned. So it is only a 1 day per week, so you can utilize that. And on top of it, if you have any doubt, you can ask. So this one is the FM signal. Now this is the amp. Yeah, question.
Ma'am, can you explain that spectra of phase modulation little bit? How we have plotted that phase modulation? Yes, ma'am. Yeah.
Yeah, phase modulation. Wait, wait. So I think in this class I didn't plan for phase modulation, but yeah, I can draw for you. Phase modulation. Oh, no, I haven't. So we have to see the phase and vary that phase. No issue. Let us see. We can draw. So even if I don't know, I can draw for you. It's not like that I cannot visualize. So let us see how we can visualize this. It was a good question. So suppose the message signal looks like this. So I'll write here MF F. So it is time domain signal it is representing. So we have to change the frequency in time. So that is an issue. But yeah, we can do MT. So whatever we are seeing the practical exposure in time domain, but in frequency domain we see the shift in the spectra. So yeah, the phase of this one is 90 degree and this one is minus 90 degree. Let us assume, yeah, it is not properly drawn, but yeah, let us assume. So after the carrier, suppose this one is a carrier. I must say the phase modulator signal must be similar or similar in looking with respect to a frequency modulation signal, because you know theta is equals to omega t 2 pi, and you know the relation between these two. Theta t is equals to 2 pi integration of fi dt. Theta t is equals to 2 pi fi t dt. So let us draw this phase modulated signal. I'll use a different color. Then
And this will be FM signal, right?
yeah, yeah,
This
yeah.
one.
I'll just integrate it. Then we will get a phase, phase signal.
Okay.
So how we will integrate it? The integration of sign is what? For a particular duration, not for a whole. Integration of sine for a whole is 1 over a period, but it is not a period.
Yes,
Integration of
ma'am.
sine is a cos, so we'll get
Yes, ma'am.
different, right? And if it is cos, you will get sine.
Okay.
So you have to think like that. If it is sine, then you get cos. Cos will start from above, like this, and sine will start from below, 0. So here you will get integration of sine is cos. And using this formula you can listen. So phase modulation looks similar to frequency modulation because it is a variation in phase itself. So you have asked a very good question. So this will looks like this. So
Ma'am, can we go back? Yes, ma'am. Little. No, ma'am. That yes, ma'am. Here only. That message signal. When suppose this message signal amplitude is constant, ma'am. Little bit upper side was the message
okay,
signal. Okay, ma'am. So here in the message signal, when this message signal spectra is constant, At that time, if we are phase modulating it, then our phase will be constant there. Means there will be only the phase will be there. Whatever is in the carrier frequency, there will be no phase from this message because of this message signal, right?
Yeah, yeah, yeah. Uh-huh. So you are saying then that this frequency, whatever the frequency of this carrier, it will be added.
Yes, ma'am.
Hmm.
Yes, ma'am. I'm just saying that only this phase will be added when this is changing at these points where it is going from 1 to minus 1, right? This
Yeah, yeah,
message signal is changing. So at those points only the phase of carrier will change. It will remain same. I think it will happen like that.
yes, you can say. It will be.
Okay.
Yeah.
Okay, ma'am. I got this idea.
Okay, okay. So, in the frequency modulation generation, I think the difficult part is of the indirect modulation, indirect method, and you should know where it is coming and how it is coming, the
Ma'am,
equations. Yeah, KP, huh?
excuse me, ma'am. Ma'am, what will be the spectrum of phase modulated signal? Like time domain waveform, we understood, but what about frequency domain representation?
Yes, yes, yes. Yeah, we can write. So, STPM is what? AC cos 2 pi FCT plus KPMT. So let us write this cos 2 pi FCT plus KP into AM uh, cos 2 pi FMT AC, and this one is this. So if you take the frequency over this one, Fourier transform, sorry, Fourier transform, then SFPM, how it will be? The Fourier transform of cos is what? Is this one, right?
Single line. Yeah,
Yeah,
yeah.
cos AC by 2. Yeah. So this frequency is this one. Suppose frequency is F1. It will be F1 and it will be minus F2. And this is having you have to, sorry, I cannot plot this right now. You have to use cos A plus B, right? You should use cos A plus B. You should use that. So if it is in the simplest form, you can plot. It's not an issue. Cos, this will be A, cos A plus cos B is what? Tell me what is the formula cos A plus cos B?
Cos A cos B minus sin A sin B.
Hmm. Yeah, minus should be there. And cos
Ma'am,
A
we
plus.
can write it in the form of a Euler formula, exponential raised to the power this whole term.
Yeah, but I'm writing, why I'm writing here in this formula, because the Kirti wants to plot the spectra of this. So we
Ma'am,
should write.
actually, I have not seen spectrum of phase modulated signal in any book, and I'm like wanted to see like in FM there are multiple side bands, right? Uh,
Hmm.
Frequency spectra of
Infinite, we
FM
say
consists of
infinite thing.
infinite
Huh.
side band.
Yeah.
Yeah,
Yes.
and we are dealing with base with the help of Bessel functions. We are plotting the frequency domain frequency response of FM signals. But
Yeah.
what about phase modulated signal? So I just want to know that.
Okay. Yeah, so I can also plot mathematically after solving around a lot. We can get a simplest equation and we can plot. But yeah, in frequency modulation, we are plotting through a Bessel function, and we have solved they're having ideally infinite spectra. So I'll suggest you just don't try to look PM and FM as a separate modulation. These both are angle modulation, and there is relation between this one angle modulation and phase modulation. So wherever you are getting frequency modulation, you can just integrate it and you can get the phase modulation. So try to look in that. So if suppose you have the spectra of frequency modulation and it is somewhat in decreasing, Uh, so you have to integrate it. How we can integrate practically? So in fact, if we are not able to do, you can write that equation in the internet graphing tool, and you can see the what is the integration and what it should look like a PM modulation. So I want to also you to suggest how the PM modulation is getting, like how PM is generated. In the generation part, you'll find in some books, I think BP Lathi, Kirti, have you seen this Lathi phase modulation book part?
Not actually exactly. No, ma'am.
Madam,
Ma'am, generation is okay, but they have not mentioned the frequency domain, like a spectrum of PM. So that way I was like,
Yeah, the thing is, the frequency domain you will have F, but in the phase domain, if you are plotting with respect to 2 pi F, which is theta, then it will be, we can plot PM with respect to 2 pi F. We can plot with respect to 2 pi
okay.
F. E- yes, KG Krishna.
Madam, one interpretation I have read is that frequency is nothing but rate of change of phase.
Yes,
So if you
yes.
take that interpretation and what you are saying is integral and that works, that
Yeah. Frequency is nothing but a rate of change. So whatever you are getting as in frequency modulation, if you integrate it, like sir was saying, yeah, it is very true. I have explained this one, this part. Sorry, where is this part? Yeah, this part. This is very important. It is theta is equals to omega t is equal to d theta by dt, and d theta by dt f is equals to this one. So rate of change, you can see this one is f, and f the theta t, the rate of change with respect to time, you will get definitely the integration of fit. So you can get, and in fact in many generation also we can generate a PM using FM and FM using PM. So if you are not able to get the spectra of frequency phase modulation, it is not an issue, because the phase modulation must look like similar to frequency modulation, similar, like changing, but yeah, that wherever suppose sine is so sine will become cosine, cosine will become sine, because integration will differs. Similarly differentiation will differs. So we can plot like that. In fact, we are not able to plot through a basic maths the frequency modulated signal, but we are plotting through a Bessel's function. So we have to see how we can convert the integration of that Bessel's function, and we have to analyze that. So that is an issue. But yeah, next class I'll look at it. And frequency is nothing but the rate of change. So you can look like that. So I think Kirti has already saw that lecture of basis function and all. So I think sir, Krishna sir, do you have any doubt in the spectra of FM sir has taught?
no, no, madam.
No, it is clear now. Question, have you saw lectures?
Yes, ma'am. Yes, ma'am. No doubt, ma'am.
Okay, so I think 1 hour left, so I'll go to the questions then. So I'll ask questions from that only. So let's see. I won't show you this one. So this one, this question, I think I'll read it. A 100 megahertz carrier is frequency mod. I want you to solve, because you have have already watched the lectures. A 100 megahertz carrier is frequency modulated by a sinusoidal signal of amplitude 20 volt and frequency 100 kilohertz. The frequency sensitivity is 25 kilohertz per volt. Calculate the frequency deviation bandwidth and modulation index. Tell me the answer. I'll tell you the formula of that. Del F is equals to what? What is the formula of del F? Frequency deviation.
Ka into amplitude A.
Yes. So tell me the answer.
Ma'am, my delta F is coming 500
Okay. One answer is 500. 500 hertz, kilohertz, what is that?
kilohertz.
Okay. And
And
what is the bandwidth, huh?
modulation index is coming out to be 5.
What is the bandwidth?
Bandwidth I don't remember formula, ma'am.
Okay. Bandwidth is given now. Bandwidth is 2 del F plus 2 F. 2 into del F plus FM.
Okay, ma'am, this Carson's formula,
Yeah, yeah,
something like that.
Carson formula. 2 beta plus beta 1 plus 1 into
2
FM.
into
Yes, yes,
1
yes.
plus 1. Okay.
Kirti, what is your answer?
Ma'am, actually, I have not, I don't have that exact formulas with me.
Okay, okay. KG Krishna sir, what is your answer?
No, madam. So don't have notebook.
Okay,
Ma'am,
okay.
1200 kilohertz, I think, bandwidth.
1200 kilohertz. So, it's very true. So, del F is 500 kilohertz. Modulation index is defined as beta is equals to del F by FM. Bandwidth is equals to beta plus 1 into FM. And you will get the values. Nice, nice. You are very correct. What you said to 1200, no? 1200.
Yes, ma'am, 1200 kilohertz.
So, yeah, you are right. So, we can calculate this. So I think there's nothing like remembering anything. So you just remember the spectra of FM, AM, and PM, and you can suppose if in exam you'd forget all those stuff. So you can derive what should be the modulation index and how the modulation index looks like. So if you are not remembering the formula bandwidth, then how the bandwidth should look like. So Carson formula. So practically we are just taking only but what is that Carson formula does?
Ma'am, what is 2 into 1 plus 1, the modulation index multiplied by frequency deviation?
Yes, yes, yes. Because in the later spectra, the amount is not there. So we are only consider this particular according to Carson's formula. So yes, it's a very good answer.
For larger values of modulation index, it will be approach delta F frequency deviation, and for smaller value, it will be equal to maximum frequency modulating signal.
Nice,
I
nice.
think.
Okay. So, how we can generate a frequency modulation using PM and how we can generate the phase modulation using FM. So these are the two block diagrams. Like PM, you have to use an integral at the input side, and if you have FM, you have to use dt by dt, and you have to make sure in both of the case Kp is equals to 2 pi Kf. Kp is equals to 2 pi Kf. How you are getting? Just it is given to homework. How you are getting Kp is equals to 2 pi Kf in both of the case 1 and case 2. So yeah, let's go to the questions. Consider the quadrature carrier multiplexing signal given as xit cos 2 pi fct minus xqt sin 2 pi fct. The complex envelope corresponding to QCM is
And it will be
Option C.
C. I think C.
yes, yes. Answer is C because it is this one in phase component plus the complex of quadrature component in phase plus quadrature component. Consider the message signal sine 100 by t. The single sideband modulated signal with lower sideband LSB corresponding to carrier frequency is this one is what? You have to find the answer.
Answer is B.
Answer is B. Okay. Pujita, hello. Fujita, are you here? Okay. Okay, Kurshid, tell me what is answer.
Ma'am, I think it will be B. It should be B.
Why you are thinking B?
Actually, ma'am, I'm getting little bit different value here. I'm just guessing.
Okay, okay. So you have to use the formula, right? What is that formula? What? Okay, Kirti has already done. What formula you have used, Kirti?
Ma'am, actually in solution they have given little different. They have used Hilbert transform. But what is my logic to tackle this question is like LSB is given, so FC minus FM should be there. So and as it is SSB and we are coming across, so whatever is the carrier I have,
Ha. So
I
what you are saying, LSB is given, huh? LSB is given. Oh, okay. So LS,
so for in SSB generation, LSB we want to identify. What I did is I have evaluated what is FC, what is FM, and that multiplied by two. So that way I will get two FC is the spectrum na, content.
yes.
So
Two
that
F. So in this way you can identify through the options. Nice way. Like you can identify through options. But yeah, the SSB generation is what? This one, na? What is the formula? AC MT by 2 cos 2 pi FCT minus plus AC m cap t is the Hilbert transform scientific basis. So this one is just a generation. So using this formula we are generating the SSB, but since it is LSB, LSB is given, so I think the plus sign is there. Yeah, plus sign is there. So you have to put this all this value, and the answer is Satyashri. So the answer is, I think it is B, and we will solve also. So this is the basic way we can go through. Otherwise, you can see the frequency and you can check through the options. But yeah, this is the basic way we can go through. See, what is empty? Empty is sine 100 pi t by 2 co what is cos 2 pi 500 t plus AC. What is the Hilbert transform of sine 100 pi t? What is the Hilbert transform of sine 100 pi t?
cos 100 pi t.
Ma'am, I
Okay.
think it is. Ma'am, it will be minus cos or simply cos?
It will be minus cos.
Okay.
So why it is minus cos?
Ma'am, I used using a spectrum analysis, phase shifted it by and multiplied it by minus j in the positive frequency domain. So value was coming out to be minus 1 by 2.
Yes. So it 1 by pi t Hilbert transform in the phase shift by a pi by frequency by 90 degree. So here it will have you will have minus cos 100 pi t sine 2 pi 1500 t, and you have to solve this. Like let us solve this. What is the AC by 2 is this? So 2 sine 100 pi t. So we cannot use 2 sine A sine B. So only we have to use sine A into cos B and cos A into sine B. You have to use that. Now, can anybody proceed, or else I'll proceed?
Yes, ma'am, it is simple sine A minus B answer is coming there. 2900 by 2.
You are coming now. Kirti,
Yes, ma'am.
have you solved this?
No, madam, but I am understanding. No, madam.
You have understood. I think Kirti and you have already solved. So let us go through the third question. Yeah. In the vestigial sideband modulation, the filter HN must satisfy the constraint.
C.
C.
Yes. So you were what the output you were getting? AC MF by 2 into this one HF minus FC plus HF plus FC. So why we are taking only one? It can be any constant, but you if it is some constant value k, then you have to design the k in the low pass filter and the band pass filter. So we are only taking one for the simplicity part. So the answer is C. Consider the SSB modulated signal with USB. His Fourier transform can be expressed as. Yeah, it is a Fourier transform question. Please solve and let me know.
Ma'am, will you please solve it for me?
Yeah.
Actually, I was unable to answer this question, and this was there in the assignment, and one more is there for LSB.
Okay, okay, okay. I'll solve. I'll solve. Question, have you
Ma'am,
solved? Yeah, yeah.
Yes,
actually,
sorry,
I
ma'am.
tried.
You
Sorry.
have solved this question.
Yes, ma'am. I solved it and just give me a few seconds. I'm going to solve it.
Okay, okay, okay. Just wait for a few seconds. Yeah, Kirti, what
Yes.
you're saying? You were not able to solve the assignment.
I did it, but my answers were wrong. I think so. Actually, I was not able to understand. Like, I know the time domain equation, but I was unable to take the Fourier transform of that. So I started with the option, and I have seen that signum function is there. So
Okay,
I have done the mathematical operations on that, and 1 plus signum function will give the frequency response of high pass filter. That way, I could able to debug it.
okay,
And
okay, okay, okay.
so that actual multiplication and what is the spectrum, that way I wanted to visualize that options,
Okay, okay.
but I could not
I'll
able.
visualize it through a graphs. Okay, no issue. Let me know. KG Krishna, you don't have pen paper.
Yeah, I have, madam. I am noting down, but this chapter I have to reread. I could not do well, so then I'm just a passive listener here, so I'm trying to
Oh,
make sense.
okay, no issues. So you do, if you have any doubt, then just let me know. Try to visualize it. Like how will it look? Mathematically we can solve, but let's visualize it and solve. So I'm waiting for question answer.
Ma'am, it will be A.
The answer is A. Okay. I have to solve and check. I haven't solved as. So yes. So let me know the Fourier transform or the first we'll see this one. Hilbert transform. The Hilbert transform HT is written as 1 upon 5t. And in the previous classes we saw what is the Fourier transform of this one Hilbert transform is minus j signum f.
Yes, ma'am.
So how will it look? It will have negative and positive. Just correct me if I'm wrong. Minus j signum f. It was minus j and this plus j. Because yeah, signum function looks like this. So it is minus j is multiplied. So sorry, it should look like this, right? So yes, yeah, I'm correct then. Minus j means minus pi by 2. Plus j means pi by 2. How? Sine pi by 2 plus cos pi by 2. E power j. E power j pi by 2. Okay. And here minus pi by 2. Okay. Now we will solve this. We know this mt cos 2 pi fct. Here it will have this formulation. Suppose mf is having this spectrum mf and this is f. So 1 by 2 this one. First term, if we say this one, if we say this one as a first term, And if we say this as a second term, so first term will look like this: FC plus FM, FC minus FM, minus FC, minus FC, minus FM, minus FC, minus FM. It should be plus. Here, first term. Now try to visualize the second term. You will have this Hilbert transform of this the message signal, and the Hilbert transform will be multiplied by this one. MT, if it MT is the input, then M cap T. And if this sign is multiplied, then we'll have this type of spectra: 1 by 2 Fc plus F, Fc minus F, minus Fc plus F, minus Fc, and minus Fc minus F. Here it will be 1 by 2, it will be 1 by 2. Yes. Why 1? Because 1 by 2, because here 1 magnitude is there. Now we have to subtract these two. We have to subtract this 2. So here directly they have written as a signum. So let us write signum itself. So suppose suppose this one is this, then we have to write signum. How they have used MT, signum T minus J signum F. So how you can calculate the Hilbert transform of MT? So you can MF multiplied by minus J signum F, because time domain it will be the convolution and the frequency domain it will be the multiplication. Okay, so you have this one. So whatever the function is this, okay, I'll write MF into minus J signum F. So here the term will be shifted by this frequency, and the term will be shifted by frequency. Now we have to see the equation which is matching with. So yes, these two terms will come from 1. I'll write here 1, and these two terms will come from 2. So let us use the equation. I think wait, add page. So we have to visualize it. Okay, the the equation is, can you spell the first equation? M question, this the spell you have already got, right?
Okay,
MF
ma'am.
minus FC
Half into m into f minus fc multiplied by 1 plus signum f minus fc.
plus signum F minus FC
Minus fc.
plus
Plus half into
F minus FC
f plus fc now, ma'am. Ma'am,
F
f
plus
f
FC,
plus, yes,
and
ma'am.
1 minus
1
signum F
signum
plus
f
FC.
plus fc. Yes,
Okay,
ma'am.
and if you just write this F minus FC plus 1 by 2 F minus FC signum F minus FC plus 1 by 2 F plus FC minus 1 by 2 signum F plus FC into F plus FC. So we have got through the graph itself. So let us write this: 1 plus F minus FC plus 1 by 2 I'm writing these two terms together: F plus FC plus 1 by 2 F minus FC signum F minus FC minus 1 by 2 signum F plus FC into F plus FC. Okay, so these are from 1 and these are from 2. Okay, so I have plotted 1 and plotted 2. So this term, it will be added, right? Because here it is in addition, 1 and 2. So here the term you are getting through directly from 1, and here the term you are getting from 2. Why it is opposite with sign f plus sc? Because in term 2 the negative sign was there. So it will be multiplied by negative sign. So it will be negative and positive. So I'll write, wait, here you will get this one, and negative somewhat. I think it won't collide. It will be here, and here it will be like this, and spectra will look like this. Output spectra S SF F. Here these two terms will be multiplied by signum, and these two terms will be 1. So here it is 1 and second. So you are getting this one. You're just plussing it. I have plotted what I have done. So I am telling you. So I have plotted first one, first term. It is simply this multiplication, and the second term. In the second term, you know the Hilbert transform will be the convolution with respect to 1 by pi t. Okay, so in the frequency domain, it is a multiplication of the Fourier transform. So mf into minus j signum f. So since it is multiplied with the sign, so it will be shifted with positive spectra and one with negative spectra. Right? You know the spectra of sign. It is an impulse and niche downside impulse. So it will be shifted like this. You are getting this, and it will be multiplied by minus. Here we are now multiplied, and we will plus 1 and 2. 1 minus 2, and we'll get this spectra. And if you write in mathematics, you will get this spectra. Kirti, have you got this point?
Not clearly, but a little bit, madam.
Okay, first, you know what is I'm telling, the first you will get
Yeah,
this,
yeah, yeah,
second you will get,
understood.
yeah. So I have added these two. I have added these two, first and second, with a negative sign, because here it is with negative sign. First, you have to understand, if you are not
Yeah.
getting anything, just understand what the Hilbert transform look like. In this question, I also didn't solve this one, but I took this question. But this Hilbert transform, I was taking how to can I do? But you know, Hilbert transform is just a convolution with 1 by pi t in the time domain, and multiplication by 1 minus j signum f in the frequency domain.
Yes.
So you will get, okay. The impulse response of the standard Hilbert transform is
Minus
1
this
by pi,
and
1 by pi t.
1/2.
yes. So you have just right. And it is a linear system in case.
Ma'am, I have one doubt related to last session.
Yeah, yeah, yeah.
You asked us to do this transform of Hilbert transform of using gamma function mathematics.
Yeah,
Okay.
did you
So,
solve?
no, ma'am, I gave it 2 hours, but I couldn't get answer. That's why I'm asking.
Gamma function. So in that actually it is a lengthy process. Like where did you start?
Ma'am, I actually started from its direct Fourier transform formula, and I was trying to get it somewhere into gamma function form, but I couldn't get any. Gamma function at zero, it is undefined actually. So
No,
I
the
couldn't go
gamma
any further.
function. What is the form? What formula of gamma function you are using?
Ma'am, t raised to power n minus 1 e raised to the power minus of.
Minus t.
Yes, ma'am.
Okay,
This
okay.
one only.
So this
Gamma.
is to gamma t. So yeah, I think in my BTech I have solved this. Okay, I'll check it whether I'm getting it or
Okay,
not.
ma'am.
I'll let you know. But yeah,
Okay.
it is very complicated. Our sir was also giving this as a question, as a homework. So yeah, you can solve it. Otherwise, you have other method also. So
Yes, ma'am. Actually, I tried doing it. That's why I'm asking. I couldn't get any
okay,
further
okay.
from
Nice that you have
it.
tried.
Yes, ma'am.
Okay,
Okay, ma'am.
complete. Consider the passband signal xt with the Hilbert transform as calculate the complex pre-envelope of the signal. Can you answer that?
Ma'am, B, I think B, XT plus.
Yes.
So, what is the pre-envelope?
Pre-envelope is, ma'am, we multiplied the positive frequency 2 times. It's
Anybody else try want to try it? Like, okay, Kurshid, you are saying we are multiplied it. So by doing,
Negative frequency. Ma'am,
okay,
actually we have a pass band signal, okay, which is not
okay,
centered around origin in frequency domain. So we want to do operations on it by making it somehow baseband signal. So we go through this step. In pre-envelope, its negative frequency component vanishes, positive frequency component becomes two times, and then when we shift it to the origin, we get a normal baseband type of signal that is complex envelope, and this comes in between this process, pre-envelope.
yes, yes, you have answered very correctly. Yes, yes. So that the formulation the sir has used for multiplying with its signals, and you will getting two times or negative signal vanish, negative frequency vanish. So
Yes, ma'am.
like and we also use post envelope. The sir has said in this about this.
No, ma'am. No, ma'am. Nothing about post envelope. Only
Okay,
pre-envelope and complex
okay,
envelope.
okay. So the formulation for that is this one. Okay. Consider
Ma'am,
yeah, yeah.
ma'am, actually that concept of pre-envelope and complex envelope, can you please throw some light on that? Act-
Okay, okay, I'll tell.
I just feel like when I saw the video, I feel like it's just a mathematical treatment. Now Khurshid said something, so a little bit I could understand. Like passband signal is, we want, our intention is to convert a passband signal into baseband signal.
Yes, 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 so that we can do operations on that.
Okay, very heavy concept, ma'am. Actually,
Yes, yes, yes. So I included this in the second part. Wait, I'll check. So E bars formulations. There are methods. I think down.
why we want to make it like this, like passband signal into baseband, like at the time of demodulation, either recovery of original signal, frequency translated signal.
Yes, yes, but that is also having the spectra at negative frequency, right? We don't want the
Hmm.
spectra at negative frequency, which is unfeasible.
Right.
We are considering only the bandwidth at positive frequencies. So that's why we want that. So I think spectrum of FN signal sir has taught. Where in what class sir has taught? This Bessel's function.
Ma'am, actually, it is before that angle modulation. Contents are before angle modulation.
Okay.
We after VSB, like around there
Sir,
only.
it's okay after BSB. So I think I don't have notes for that.
Ma'am, I
It's
think
okay, ma'am.
after this lecture, sir.
After this lecture is also there lectures. I thought this is after this lectures we'll have annual moderation and all. Otherwise, I must have taken that in my account. But I thought this is a small portion sir has covered. How many lectures sir has
Three.
covered this pre-envelope and
Two
all?
or three.
Two or three. Okay, then the next lecture the first class in the initial only I'll deal with that.
Sure, ma'am.
Yeah, I'm not getting now. So
Yeah, it's
otherwise,
okay, ma'am. Actually, just I want to understand practical significance. Like, what is the importance of that concept in communication? So that way, I want to understand.
yeah, yeah, and it's very good that you are courageous to know like what is the practical significance because it's very important. Sometimes we just study, 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 but we don't know where it is used and all. So we should know where it should be used and how why we are studying in fact. So nice. I'll take to my homework. I'll do that. So I think yeah, it's again a question from pre-envelope sir has taught in things. And consider the passband signal xt with the Fourier transform xf. The Fourier transform of the complex pre-envelope of the signal is. So you should know the formula for that. What is the complex pre-envelope of the signal?
Yes, ma'am. Last one.
Last one. So how you have solved?
Yes, ma'am.
How you have solved just by seeing the this
You know,
huh.
yes, ma'am. Like I told, how we arrive at this thing, xt plus jxt, what it does in frequency domain. So that's how.
Okay, that is fine. Like to XF greater than 0 or 0 otherwise, because we don't require frequency at negative negative frequency, which is not feasible at present. So it is not required. Kushit, can you tell me the formula for the pre-envelope? Like we multiply it with something.
Formula for pre-envelope, it is simply, ma'am, xt plus j time x hat t, and then
No, it
the,
should be multiplied by e power something, right?
ma'am, then it becomes complex envelope actually. Pre-envelope,
Okay,
pre-envelope, then multiplied by that it gets shifted, then it becomes complex envelope.
okay.
So
Got it, got it.
okay, okay.
So E power will be used for complex envelope, otherwise it is used for pre-envelope. Again, I'll deal with this complex and pre-envelope in the next class, no issue. So, yes, it is again the same question, I guess. Okay, my mistake. So this one is the answer is this one. So I have solved this properly. You should see previous. But please solve this question. This is very important. And please solve with USB also. So yeah. Hmm. Tell me the answer for this. In coordination carrier multiplexing, how many messages are transmitted in parallel over the same channel?
Two.
Ma'am, two.
Yes, yes. One sine, another one is cos. So why we are saying quadrature? Because it is in a 90-degree phase shift. So can anybody let me know where the QCM is used? So we have talked about SSB, VSB, DSB, AM, and also FM, where it is used. We all know about this, right? So where is the QCM is used? So I want you to see some references for that. But yeah, it is very interesting. So find where QCM is used here. QCM is used. It is used. It is the homework for you. So in the next class, I will deal the pre-envelope and converse envelope for a while, and then where the QCM is used. So I know now, but I want you to search first. So you should be courageous enough that you can see where it is used and how it is used. So yeah, this one is this. Yeah. Let's solve this question. Consider the message signal mt is equals to sine 2 pi fmt modulated using DSB-SC with carrier cos 2 pi FCT. This is demodulated at the receiver with the carrier the cos 2 pi FCT. That was a phase offset of this one, followed by low pass filter. The resulting output is. You saw that Costa receiver, right? We saw how the cos phi should be.
Yes, ma'am.
So yeah, it is from that part only. It is from little back from back part. But yeah, you can solve. You should not forget anything. Yeah, you can forget sometimes, but yeah, after revising and all, you should not at some point you should be in that phase that you should not forget anything.
Ma'am, it will be first one. First one.
Okay, did you solve or just check?
No, ma'am. No, ma'am. I solved here.
Okay, okay.
Multiplied it, then applied simply formula, and then LPF higher frequency. I simply did that. Ca- Cancel them out, and then I'm getting this.
Yeah. Ramasri, you are new here. Can I know about you? Hi, Ramasri. Hello. Okay, no issue. Kirti, did you solve?
Ma'am, I'm doing.
Okay.
Madam, one general philosophical question, nothing
Yes,
to do
yes,
with subject. I
yes.
am basically a mechanical engineer, and I'm a whole career. I am now retired, and I doing this electronics communication out of my interest. I did actually PCS two, uh, of this course earlier. Okay, that's last
Which
semester.
course? Which course? Can you
Uh,
repeat?
the same thing, principles of communications too.
Okay, okay. You have done that second, huh?
I had done that.
Nice, nice.
And now I've done that. But you see, I tried my best because to there's a lot of mathematical juggling between time domain to frequency
Yes,
domain
yes, yes,
back
yes,
to
yes.
this. So my mind is getting exercised. Okay, so I'm telling you, this is the first time. I don't know. See, I'm not at an electronics engineer at all by degree or by profession.
It's
Okay.
very like I'm very shocked to know that you're a mechanical engineer and at this age you are doing that. You are
Yeah, I
visualizing.
was a mechanical engineer, whole profession I worked in software. Now, out of interest, I'm doing the electronics. But one question is that I find this all these things, this modulation, demodulation, mixing, and so,
And receiver and all.
everything is filters. Everything is related to transformations and filters.
True, 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 true.
So even
Everything is related to signals system. So
yeah,
you should know signals system at the same time. So I in the initial classes also I used to say that please don't remember about. So you were saying that's why I used to get shocked. Like how do you know this DTFT, DFT? You have already done, right?
yeah. So
Yeah.
everything in fact I'm doing that also, signals and systems also, course of the same parallelly
Okay,
to
okay.
this.
Hmm.
Okay, so everything boils down to ultimately the is a filters. Okay, filters or modulators expressed in mathematical terms. What is bothering me is we never get to see the real life. Maybe because even in some books they use MATLAB simulations, but in real life, as one of our colleagues saying that trying to visualize. For example, it took me 2 weeks to understand what is a negative frequency. Okay,
Okay.
because I come from mechanical, everything I see in the real world, and we can connect something moving.
Yes,
Frequency
yes.
I understand, but negative frequency, where did it come? Did it come from a mathematical imagination of complex variables, or somewhere you mentioned that you remove negative frequency, negative is adds up to bandwidth.
Yes, 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 yes,
Yeah,
yes.
it requires a lot of, I think this is a course, if anyone is doing a lot of abstraction analytical skills will go up. Basically everything is formulated using mathematical models, and from models actually we are devising all these modulators, demodulators. In fact, modulator, demodulator is nothing but all these things implemented in software.
Filters. Ha, ha, yeah, yeah, yeah. True, sir.
So
It's very sir, you can visualize the filter. Have you tried to build the filters? Have you ever listened about heard about this JVC filter, butterscotch filters and
yeah,
all?
yeah, I heard about it. Where so only thing is, so madam, as I keep reading it, even though I'm keeping advanced reading, I get some abstract, some idea. So I understood filter as something which removes unwanted frequencies, and since ideal filter is not practical, that Butterworth filter is one where there is some tapering off, and
Has been
something.
yes,
So
yes,
yeah, Chebyshev, but they're all analog filters, right?
yes,
Implemented.
yes, yes, yes.
Then correspondingly, yeah, that is also interesting. So we first do in analog filter, then go into the digital domain,
Digital filters.
we digital filter, and so again come back to the analog also. Somewhere you know,
True, true, true.
somewhere I saw that that. So I know that even if I don't pass this exam, but I'm sure that I'm going to repeat to get my real hands on this whole.
I'm very pleased to know these things about
Yeah,
you, sir. It's very
yeah.
Kursin and Kirti, you can actually learn from sir. Like he's a mechanical engineer and his story is very inspiring. Can I ask one question? What motivates you to learn electronics engineering?
Madam, one thing. Well, when I'm in college, I was interested in electronics hobbies. Okay,
Okay,
so
okay.
because electronics is wonders, right? The signals, anything, wireless communication, radio, and transmission. This I'm 60 years old now. Okay,
Yeah,
so
yeah, yeah.
but unfortunately, I could not get into electronics. I got into mechanical, though I got 9 point CGPA and everything. Then Then because of job pressures, I got into software because I had to learn software to survive. In those days, only software industry was there. So the whole career is in software vice president. I did software project management. No mathematics, madam. In business, the only mathematics you hear is plus minus divided by bar graph pie chart. That's all.
Very true,
All.
very true.
Okay. Now, because in fact, at my home, I bought a lot of. I'm a ham enthusiast also. I has a ham.
Wow.
So so I was curious, how a wireless communication work digital. So I bought some ham walkie talkies, and then I was curious. So because of the curiosity, I'm taking this course.
Nice.
Say I wonder that in digital with software, everything is done in software. Okay, that's why the cost is coming down with the digital handsets nowadays. A mobile phone plus walkie talkies, everything is digital. So all these
Yes.
filters and everything is implemented in firmware. So many wonders are happening in the firmware, and that firmware is nothing but these whatever we are studying, these algorithms, these modulation, demodulation implemented as a code, right? So
True,
uh,
true, true. Very true.
that is what actually, to get a big picture. Okay, so that's why even though I don't understand, I keep attending it. So even if I understand 10-15%, that's enough for me to make a big picture. Maybe I'll repeat it. Maybe next time I'll understand more. But if I'm in the profession, certainly I understand. Since I'm not in the profession, my thing is I should be able to comprehend how things work, at least explain like a scientist rather than saying as a black box. Okay, it's to reasonable.
Nice. Okay, okay, sir. I was not aware that you are actually from this background. And learning at this age, however, learning doesn't stop anytime, but still, it's very
Yeah.
courageous.
And I also learned Japanese. Not only this, NPTEL, I have done about 25 courses, madam, in the last 3 years,
Nice.
including Japanese language.
Sir, where did you stay? Can I know?
I am in Hyderabad. I teach part time at BITS Pilani.
Sir, I am in also Hyderabad. I'm in IIT Hyderabad.
Oh yeah, yeah,
So,
meet.
uh,
See, in fact, I tell you my curious history. See, I was working with Satyam till 2010. Okay, when Satyam blow up happened, my mind was clueless. I was technical at heart, so I don't know anything. I don't know anything. I only know how to manage software project management, software quality, and all. So, but I wanted to do something. So I went into BITS Pilani, Hyderabad campus. Then they said, "What is that, sir? You can teach here. The all young people are there." No, sir. I want to do something, activate my mind. There is only course available at that time for me. Faculty was systems and controls. I remember that even though there is electrical course in my long back 30 years back, I did this as a part of mechanical engineering controls.
controls. Yeah, yeah,
Control
yeah.
theory. Yes,
Mm-hmm.
sir, I can teach. So with adventure, I jumped into it as a challenge, and they are happy with it. They made me in the electrical engineering department. I'm not an electrical, so I had to justify myself to electrical. I took microprocess course and I taught that. Now recently, then machine data learning, data science has become a very very important course. So I also did some data science courses. Now, because the retirement, I wanted to understand how electronics work. But this course is so heavy because parallelly I'm
Yeah.
doing other courses. This so analytical rich. So if you want to understand 1 hour of the video, we have to spend at least 3 to 4 hours of reflection and homeworking to understand concept. Many
True.
times I watch a video. Suppose what is this negative frequency? I to understand really. I had to spend at least some 2 days, nights on YouTube video. Somebody explains much better on YouTube what negative frequency means.
Yeah, 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 yeah.
So actually speaking, if we wanted to learn, there are a lot of material is available. Only
True,
thing
sir.
is we require some motivation and guidance, which site, which better. But uh, so in that context, I am in the learning curve. Okay, but surprisingly, last semester I did PCS two. How could I clear PCS two? And now I am doing PCS two is advanced of PCS one, right? What we are currently.
Obviously, most probably next semester I'll teach that. But yeah, digital communication people find it a bit tough than analog communication. But I think it's not an issue, so you will learn everything
Yeah, yeah,
smoothly
yeah.
because
Yeah, yeah.
you are from mechanical engineer and worked in software part. So it's a very
No,
inspiring story,
no,
and Khurshid was
no,
also
no.
saying,
No, no, we should not think the mechanical engineering is long back. Okay, if you mind us, keep it afresh, start from zero state phase. Then
yeah,
we,
true,
if you
starting
wanted
from
to
zero
learn, you can
state.
learn anything. Why only electronics? You can learn philosophy, you can learn anything. I think open mind is what important. See, what
Yes,
we
true.
studied 30 years back doesn't make any relevance. Okay, doesn't make any.
Yeah, we
So
used to forget. Yeah,
yeah, yeah,
I'm also doing research in this part, so it's completely mathematics and all.
yeah,
So
yeah.
yes, it's
So my wife looks at my books saying that so much of mathematics. I said, this is not mathematics, this is engineering. And so you are working more harder than students. I said, yeah, I know
yes,
students are smarter because I wanted to match students. So anyway, madam, it's nice of you. So you are very passionate. And maybe at one point, maybe I would like to come visit your campus.
yeah,
I,
sure, sir. IIT Hyderabad is near here only, so
sure,
whenever
sure,
you
sure.
please.
Sorry.
And
Yeah,
yeah, it's very nice to know. Others wants to say anything, just let me know, please.
yeah. Thank you.
Yeah, yes, sir. Thank you so much. Ramashri, you wanted to say something. I saw your video on. Can you please keep it on? It was looking very good that you switched on. Mhm. Hi, Ramashri. Hello.
Hi, ma'am.
Yeah, you are be what? Can you tell me about you, like your student or what?
I am a technician job, lab technician.
Okay, so you're learning this course.
For better
Okay, lab technician.
to my
Technician.
skills.
Hmm. Nice, nice, nice. It's very good. Thank you, KG Krishna sir, so much for telling us about your story, and it's so inspiring. And one can learn if one can learn at this age, starting from the scratch. Then if we are young, this much young, we can learn anything, and it's not enough age and all. It's very inspiring.
Yeah, yeah.
Khurshid, you said this something like. He said, "Sir, seriously, you are inspiration for our generation." Yeah, very true. So it's very nice. So I think everybody must have got this answer. The answer is A, and the the solution I can do for you. Kirti, have you got the answer?
Yes, ma'am. Yes.
You have got. Okay. So it's simple modulation and then demodulation. So you will get 1 by 2 cos sine 2 pi FMT. I have solved this question in the previous sections. So you can look at that also. It's not an issue. So yeah, we would like to end the class. Anybody wants to say more? I would like to hear. I would literally it was I get impressed by sir. Like sir said so much about him.
Yeah, the only thing, madam, which makes difficult for us is related to the reality. Okay, for example, in mathematics, like negative frequency. For example, in some books also confuse. They use omega as a notation, e to the power of j omega. Some books
Then
use e.
that's why in my whole career, I used to prefer only a good book. Yeah, sometimes book confuses, but yeah, some good books will not confuse. I think if you have yeah, similar notation should be there, but I don't think a very different notation will be there. A very far different.
See,
So
for example, the Aditya sir always uses frequency domain representation 2 pi of t. But some books, when I open a BP Latin books, I don't know which books are something omegas they use x axis. So
uh,
I so that is one common. I think. See, as a student, I'm telling you from my side.
mhm.
These are the small twists, which actually tricks, which will like a speed breaker if they stop. For example, till I understand what is a negative frequency, which took 2 3 days, I could not. Even today, that I could not visualize. I said negative frequency is a creation of complex variable. Okay, it is not in the reality. Okay.
Yes, yes, yes. In fact, in bandwidth also we do not consider negative
Ah,
frequency. Huh?
okay. So So we are all in a real life we are all used to representing everything on the positive x-axis from zero towards right. When move something towards left, either in time or frequency, our mind goes somewhere. Okay.
So it's very nice that you have given 2 days to understand negative frequency. I think if we are stuck at some point, we should actually give us the time and
Yeah, yeah, yeah,
effort.
yeah, yeah, yeah.
Yes.
I feel because I'm also a teacher now. I'm also learning how to teach because in these speed bumps, no, if so, someone spends more time at the speed bumps, okay,
Mm,
then once you get a clarity, you can jump, you can go at speed. Okay, if you
very
get
true.
stuck, you cannot. It is like learning the tricks of swimming. Once you know the trick, you can learn on your own. Okay, you can go.
Very true, very true.
Uh,
That's why I used to say, please learn the basics. And sir, sometimes if we don't remember the formula, we should be in a stage that we can derive the formula from the basics. We should not learn each and every formula and all,
Yes, yes, madam. See,
because
I
after some
remember.
time we will forget.
Yeah,
Uh,
I remember one incident my college life. I think very old, maybe your father's generation. When I started programming in my BTech, we had a programming course called computer programming. We never seen a computer program. We never seen a
okay.
computer in those days. I'm talking about 80s, late 80s.
Yeah. I can imagine.
We had early 80s. We had never seen a computer, but we had a course on computer programming by Rajaraman using Fortran. Okay,
Okay,
so
nice.
our sir used to teach all the algorithms, sorting numbers and sorting in alphabetical order and all programs. So this is how board used to write on the board, and we used to take notes on the board. The concept of algorithm: start x is equal to 0, then set I is equal to 1, then somewhere it used to come I is equal to I plus 1. Okay, so
Yes,
that's the
yes.
Fortran program, right? Fortran
Yes,
program.
yes,
So
yes.
we were used to normal mathematics, right? We never had understanding of what is a computer, what is an algorithm, what is memory, nothing. We never seen a computer in our lives till date. We started writing a program. Oh, how come? See, in Fortran, that assignment is statement is equal to I equal to I plus 1.
Yes,
How
yes.
come I is equal to I plus 1? Nonsense statement. How can they make this? And, my mind was blowing. I asked my colleague, thing, says, no, 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 you just copy that. It will come and don't ask me. I also don't know. So we feel shy to ask the teacher, sir, because we feel that you get teacher think that we are dumb and all that. So my mind was that was like a mental block. Okay, of
Yes,
course I'm
yes.
telling you, I've written a program. I just copied from that, changed some variables, and submitted the card deck, and I got the result. I got A grade. I tell you,
Nice.
I got A grade, but my mind was totally confused and vague about what is programming. I hate computer programming. But after 2 years, when I took one microprocessors course, when I started using microprocessor kit, when I started changing variable using the microprocessor keyboard and update that variable plus one. Oh, aha, oh, this is the meaning of I is equal to I plus one. It is not a mathematics, it is updation of variables.
Yes,
That
yes.
that aha moment, I think, changed everything. Then I became a computer programmer, I'm telling you. So
Nice,
what
nice.
I'm saying is for students like me, like middle benchers, who get confused. Sometimes these speed bumps, get clarity. Then we get aha. Then we get enjoy the course. And
Yes, yes, very true.
in a regular class, what happens is the faculty goes at his own at common speed, assuming that everyone knows and everyone knows. But some students like us will pull our hair and we middle bench confuser, and we may get A grade. Actually, getting grades is the most easiest thing in the world. Getting A grades,
True, true.
but
But yeah, we should know the basics and all.
yeah, so
Mhm.
that is what my insights actually. So I am trying to get actually. In fact, I got some insights from you also. Like for example, on negative frequency from the YouTube I got, and one insight is frequency is nothing but rate of change of phase. Okay, that is something which is a revelation to me. I thought frequency is a different independent parameter, phase is an independent parameter, amplitude is an independent parameter. But
Yes, 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 yes.
both are three independent, right? When you make the statement, frequency is a rate of change of phase. That means something to keep reflect upon it. Yes, it is uh, yes, because it's a part of cos function, f function. Like that, so whenever I come across that, I used to make notes in my notebook. So next time if I happen to teach, I focus on the speed bumps first. Okay. Uh,
Okay, nice.
so that's why I'm attending. So frankly, I not no, I could not follow. Even the 80% of what you said, but I am tracking. Okay, what I need to know, what are the key concepts? Maybe yeah. Let me see whether how can I fit. Thank you very much, madam. So
Oh,
sorry for.
no, no, no issue. We actually get inspired by you. And even if you are getting 15 or 10% of whatever I'm teaching or whatever the sir has taught to you, so it's very actually a very great achievement for all of us because like from your perspective, it's very difficult. And like, yeah, we have all
Actually, the sir is teaching very beautifully.
yes,
Is
yes,
going
yes.
logically by writing everything clearly, the deriving everything and highlighting important things. A very beautiful way is teaching. Uh,
Very
uh,
true, very
uh,
true. Sir
uh,
is my favorite, Aditya
yeah,
Jagannatham sir.
very,
Yeah,
very,
yeah.
very beautiful one. Yeah. That's why I'm able to do actually PCS2 course in the last semester. Okay, so yeah. Thank you, madam.
Yes, okay. Okay, then we will end the class now. So we'll meet in the next class. Thank you so much.
Thank you, ma'am.